actually. Like one of them is, oh, sorry. I'll start again. Yeah, so thank you for the invite. It's always great to talk about sharpness. And then today I'm going to talk about actually two of my works. One of them is about how sharpness-aware minimization minimize sharpness. And at the end, I will also briefly talk about my other work on sharpness and how it connects to generalization. Today's we will roughly go through the background on implicit bias, sharpness, and also the manifold assumption, which is the central assumption of this work. And then we'll cover some results on how sharpness-aware minimization actually minimize sharpness, and in particular, what kind of sharpness that does they minimize. And we will see that there is actually a surprising relationship with the batch size you choose, and actually with different batch size, sharpness-aware minimization will be minimizing like completely different things. And then at the end, I will talk about the relationship between sharpness and generalization. So to put some background, people has been curious about implicit bias for a while, and the reason is because has been work showing that neural networks have capacity to memorize like even random labels, given that the data set is small enough. However, this means that like traditional method like uniform bound will likely fail in terms of like capturing the generalization of neural network, because like we do know that while they can memorize random labels, when they draw trend on the true label, they can typically generalize. And this means they must have been finding like they must have a bias towards generalizing solution versus the brute force solution that just memorize everything. And to visualize this, you can imagine there is like two types of minimum. One of them is like the memorizing solution, which cannot generalize at all, which is the yellow star here. That has very low training loss but very high validation loss. And there are also a type of minimum that can actually generalize, which is the blue star. And the model will typically prefer the blue one versus the orange one, which is also the reason why like a neural network can succeed in some small data regime like CIFAR 10 or ImageNet. And the reason behind this is still widely unknown, but people have developed many theories around optimization and neural network architecture to try to capture why the models can actually choose the generalizing solution. And among the implicit bias, a very popular example is sharpness. And the intuition of sharpness is very clear. It's actually imagine that every point is a imagine that there is a loss landscape, and sharpness is just about how flat the minimizer is. So essentially, how high the loss is around the minimizer I found. And there has been proof it has been proved that SGD will typically prefers a flat minimum versus sharper one, at least empirically. And also there has been some theory showing that this is likely the case. However, there are actually many different ways to make this term precise, and I will briefly introduce two of them here. And the first one is about average direction sharpness. This means that I will choose a point x, and then I will take a random perturbation of like a radius rho around this point x on the weight space, and I will try to see how the loss increases on this sphere around the weight x I have found, and I will take the average of it. And there's also a more there's also another version which is called worst direction sharpness. And in this case, instead of finding the expectation on the sphere, I can also try to find the highest point around the sphere, highest loss point on the sphere, in order to minimize like how bad my loss. What's the worst case that my loss can be if I actually perturb my weight by a small radius? And at least it's kind of intuitive that like people has the intuition that like flat minimum can actually lead to generalization, because you can imagine that when you drift the loss a little bit from training loss to validation loss, a flat minimum seems likely to generalize better, because all the weight around it is also of like low training loss at least. And there are like a very successful method developed after this idea, which is the sharpness-aware minimization. And the idea behind sharpness-aware minimization is just that we want to minimize the worst direction loss, worst direction sharpness plus the loss, and then in order to reach better generalization. And so concretely, sharpness-aware minimization, or SAM, is just this algorithm. that in this plot you can see that my original weight WT, and I will first take a gradient ascent instead of descent to get to a adversarial point W adversarial, which is on the direction of my gradient, but and I will normalize it to take a step of radius rho. And at this new point W adversarial, I will take a gradient, but instead of like taking the gradient at this point, I will like move the new gradient back to the original point, and then to take a new step. So essentially, this is the formula behind sharpness-aware minimization, and I will explain why it is why it is like parameterized in this way slightly later. And for it at all, like try to develop this method in order to minimize the worst direction loss, which as written here in the red equation. And but like as you may guess, like these two are not actually fully equivalent, and in fact, two heuristic approximations are used to make like to try to make this goal realizable of minimizing the worst direction loss. And the way they do it is through like the intermediate loss called ascent direction loss. And the worst direction loss, as in the red line here, is very hard to compute. And the reason behind it is that you need to compute V in order to you need to compute the V that actually try to maximize the loss on a sphere, which is an inner optimization of its own. And in order to solve it, you need to run at least you need to run multi-step of gradient descent. Freud et al. Believe that it's likely sufficient to only consider one step gradient ascent, and then they actually just take the gradient at x and then just project it to the sphere and try to say that this point, the first order approximation, is already good enough as a approximation for L row max. So we will call this new loss, which is the loss at the point of the ascent of after the gradient ascent, the ascent direction loss. However, even the ascent direction loss, when you take gradient of it, you can imagine that you will actually like take gradient of this gradient term as well. So it actually involves the gradient of gradient, and it is also very expensive to compute. You will likely need to take like 3 to 4x more compute in order to take the gradient of gradient instead of just the gradient itself. So therefore, they just propose to use another approximation, which is that I will take the gradient, but I will stop gradient at the point where I take the ascent. So like this is just a plan like a gradient step. Well, just that the way that I take gradient is no longer my original weight, but it is the way that at the ascent at the point of ascent. However, in fact, actually, we will show in our work that both the approximations are not correct. But surprisingly, it also makes a coincidence that like the two negative actually make an alternative that the full batch SAM is indeed minimizing the worst direction loss. That we will also show this later. But in order to approach this problem, we need to first introduce the manifold assumption, which is the key assumption that behind our theoretical analysis. And I actually show you this plot like early on like how to visualize the neural network landscape. But actually, this is actually a trick of like the low dimension. So here I'm also only plotting a one dimension weight. In fact, the weight is very high dimensional, and the classical viewpoint is actually not very precise. Instead, there is reason to believe that at least around the neighborhood, all the minimizers are actually connected as a manifold. And the reason to show this, the reason why this may be the case, are twofolded. First, there are theoretical evidence that especially when neural network generalize, when there are much more parameters than number of data, then you are actually in an over parameterization regime that like and then in this over parameterization regime, you can apply the implicit function theorem, assuming that your neural network activations are all smooth. Then like a manifold must exist around the minimizer at least locally, such that every point on this manifold will also be a minimizer of the original loss. There's also empirical evidence behind this, which is mode connectivity. And people have found empirically that if you train two neural networks with like two different random seed, but on the same data, the minimizer you will find will be path connected. So this is a necessary condition for this to be a manifold. But the meaning of this is that there will be a sequence of points that like all of very low loss and these 2 points and this sequence of points can actually connect these two minimizer. And this assumption is adopted from like the earlier work by my co-author Zhiyuan Li about what happens after SGD reaches zero loss. And in that work, a useful framework like discussing the optimizations dynamics on the manifold is established. It may sounds kind of counterintuitive to you about what does the optimization dynamics on this manifold mean, because like this is already the point where the loss is already minimized. So like it's actually not about optimization in the traditional sense. It's more like if you run your optimization algorithm on this manifold, near this manifold, which the where the loss is already near minimized, then like what will happen to your weight? And in this case, this is a simple isolation for the implicit bias that I'm talking about, because now you don't have the pressure to minimize your loss as the loss is already close to minimized. And what will take place, what will actually matters, will now be the implicit bias. And and the previous work considered a simple example of like of the continuous limit of SGD, which is just the equation written written here, which essentially you will have a signal which is the gradient, and this signal term at near the manifold will be very small. But at the same time, you also have a noise term, which is introduced by, for example, the batch noise or the label noise. And in this case, if you are at the point near the manifold, then you can actually start to consider the projection of of your weight on the manifold. So like your original weight may still have a small but non-zero loss, but and a small but not minimal loss. But you can also consider a nearby point which has a minimal loss. And so this framework will try to track how will this projection evolve on this manifold. Um, and there will be two dynamics essentially. There will be a so-called fast dynamic or normal space dynamic, meaning that perpendicular to the tangent space of this manifold, the weight will evolve as if you are minimizing a quadratic function. And the reason behind this is that you can do a second order approximation near the projection x star, and the model and your optimizer will just do like an optimization with noise on this like normal space as if it's optimizing a like quadratic function. And you can prove that in this case, in this case, you can actually compute how will the weight around the projection evolve as a distribution. And once you compute that, there will be a dynamic that essentially once you know the distribution of your weight on the normal space, this distribution will actually cause a deterministic drift on the manifold due to some Taylor expansion that looks like this. It's not important to know the concrete detail here because I will detail the calculation of them later. But essentially, this is like your stochastic dynamic around the normal space will actually cause a deterministic drift on the tangent space of the manifold. So there will be a very slow, in fact, like roughly speaking, you will move at the rate of eta square, where eta is your learning rate. There will be a slow dynamic that like gradually drift your projections on the manifold. But what's important is that this drift is actually deterministic, so that on the manifold you are actually running an ODE. So there's a nice duality between the original as the stochastic dynamic on the original weight space and the deterministic dynamic on your like on the manifold. And so going back to Sam, we already claimed that they are both wrong, and but there is also but by coincidence or more or less, the full batch Sam is actually minimizing the worst direction loss. And also there's one thing we call one Sam, which essentially means that instead of taking the full batch, you will do what's more typical in deep learning training, that you actually take a stochastic batch. And here we in particular assume that you just train with batch size one, and that hence the name one Sam. And you will take the one batch size and then only take gradient ascent on that particular one batch, and also only take gradient on that one batch on the same one batch after the ascent. And then this one Sam will actually is not minimizing the worst direction loss anymore, and it's in fact minimizing the average direction loss instead. And both of these are kind of implicit and not actually following the calculation of Forest at all in the original work. And so just to recall, we have now three different definitions of sharpness and also the corresponding laws. And there's this ascent direction loss, which is the loss at the point of gradient ascent. There's also worst direction loss, which is the highest loss at the nearby sphere. And there's all average direction loss, which is the expectation of loss on the nearby sphere. And we will first consider the explicit bias, meaning that if I actually have some oracle that minimize these three laws, what will happen? And first, the first thing we can show is that for small rho, the convergence point of all these three laws will be like the minimizer of all these three laws will be near the original zero loss manifold. So will be also it will be very close to an original minimizer of the original loss. And when you take rho to zero, you can actually show that minimizing these three sharpness-aware laws will be also corresponding to minimizing the corresponding function of Hessian on the manifold, and they will actually be corresponding to minimizing different function. So like they will in the first version, there's this worst direction loss, which is about like which actually corresponds to minimizing the highest eigenvalue of the Hessian at the minimizer. So among the manifold, like different minimizer while having the same loss will have like different Hessian function, and the Hessian function will have different eigenspectrum, and the worst direction loss will be corresponding to minimizing the highest one. And ascent direction sharpness, which is the loss that the SAM originally want to minimize, if they actually take the gradient like properly. In this case, they are actually just it's actually minimizing a very weird term, which is the minimal non-zero eigenvalue of the Hessian. And finally, the average direction sharpness is the one that is the one that actually will minimize the trace of the Hessian. So you can imagine this is average. This is minimizing the average spectrum instead of the worst case or the best case like eigenvalue. So like at here you can already see that the second step of Four et al's calculation is wrong, because like if you actually approximate the worst direction loss with the ascent direction loss, you're actually minimizing a completely different thing than you're actually introducing a completely different implicit bias than you originally want. And you are, instead of minimizing the worst case sharpness, which is something that intuitively feels good, you're actually minimizing a very very weird term, which is the minimal non-zero eigenvalue, which where the interpretation is much less clear. And here the takeaway is that like actually the small difference between different regularized laws can cause very different implicit bias. Although you can actually prove that ascent direction sharpness and worst direction sharpness are close in some cases, like they're in terms of value, their minimizer can be very different. And actually, the way to see that ascent direction sharpness is minimizing the minimal eigenvalue. The minimal non-zero eigenvalue is also very easy. And the way to see this is just that you can take a Taylor expansion at a minimizer, and then once you take the second order Taylor expansion, the first order term will go away because when the rho is very small, the point is already close to the original minimizer of L, such that the first order gradient will vanish. So like you only need to consider the second order term, which is this quadratic function with respect to v. And actually, once you also minimize of course v, you can see that the this term is actually minimized when v is aligned with the smallest eigenvalue around the Hessian. And there is some particular reason that v cannot actually be tangent to the Hessian, even if the Hessian is not full rank. But I will skip the technical discussion here. But the key to see here is that there's no force that will enforce that v to be aligned with the highest eigenvalue, the highest eigenvector to the Hessian, so that this will not be the worst case sharpness that people originally want to minimize. So here we already show one arrow, but we will actually show that full batch SAM can minimize the worst case direction loss. And this will show that the second thing is also an arrow. And to see this, we'll actually need to consider a dynamic analysis instead of just a minimizer analysis. So we'll actually need to track the optimization dynamic with respect to SAM. And there will in fact be two phases, where the first phase is less interesting, which is just that the loss will be minimized, the original loss will be minimized, and then the point will converge to a point, and the iterate will converge to a point near the manifold. And the second phase is more interesting, in the sense that we will show something that is very like briefly discussed over SGD, like early on, that for SAM you can also compute an ODE on the manifold, and we will show that ODE is actually minimizing the highest eigenvalue of the Hessian. And the first phase, as mentioned, is it's just that you when rho and eta are like small enough, you can find that fallback SAM will be tracking the gradient flow. Will be tracking the gradient flow as that you can will this like original SAM update when all the hyperparameters are small, just as a discrete version of the gradient flow. The second phase, however, is kind of non-trivial, and we will actually show that on the manifold, the loss the iterate driven by SAM will be roughly tracking this Riemannian gradient flow, which is first you take the gradient of the highest eigenvalue of your Hessian, and then you project that gradient back to the manifold, so that the iterate will keep on the or will keep to be will be kept near to the manifold or on the manifold in the limiting cases, and then your iterate will actually be tracking this Riemannian gradient flow until it reaches a local minimizer of the highest eigenvalue of the Hessian. So this, like combining these two phases, you can already say that fallback SAM will oscillate around will oscillate around the zero loss manifold while moving along this particular flow, and in the end, they will be minimizing the worst direction sharpness. And why it will keep moving on the manifold instead of just converging? Different from the SGD analogy before, where we have noise, so there's reason to at least believe that it will actually oscillate. Here, for SAM, there is no noise because we are considering a full batch setting. And if you consider GD, it will actually just get to a one point on the manifold and then stay there forever because there's no gradient. However, for SAM, there's this ascent direction such that there's a stand step that is normalized. So like on every point that you actually take the gradient for your update, you are actually like taking the gradient at a point that is at least of distance rho to the manifold, such that so in this case the ascent step will always provide some non-zero gradient, and this forces weight x from falling into like an arbitrary stationary point, and it can only stay around like some very special like you can only stay around some very special stationary point, which is the minimizer of the worst direction sharpness. And the second thing, which is perhaps more important, is that what actually determines this ODE. So actually this ODE does not come out of vacuum. It can actually be shown out of this again some Taylor expansion. And so in particular for SAM, like the gradient you take, the actual optimizer step you take is just the gradient at this point, at this ascent point, and then you can actually break it down into three terms after like doing a second doing a Taylor expansion. And the first point is and the first term is very small because you are already very near the manifold where the loss is minimized, so you don't have much of a gradient. And the second term is actually falls into the spectrum of your Hessian. And for the zero loss manifold, there is a nice property that the entire eigenspectrum of your Hessian will be perpendicular to your zero loss manifold. And the reason and this is also kind of intuitive because on the manifold, everything is of the same loss, so the Hessian term will disappear in the tangent space and only appear in the normal space. And this means that the second term, although it may be hard to see what it is, at least here, it's actually always orthogonal to the manifold. And you are only left with the last term, which actually will determine the direction of your ODE. And this term is just some tensor product between the normalized gradient with the third order third order gradient of your original loss. And here there are two key observations. which are like the first one is rather technical, or this is known in in some early literature that if you actually if either of if this gradient term actually align with the first eigenvector, sorry, I make a typo here, this shouldn't be eigenvalue, it should be eigenvector that correspond to the Hessian, then then actually you will see that the this term will actually be just the gradient of the maximum eigenvalue of the original Hessian. So like this is roughly an artifact of that you are this is roughly speaking that if you are oscillating along highest eigenvalue such that your gradient actually align with the highest eigenvector, then you will be actually taking the gradient over this worst direction sharpness term. And and then the second thing is that for Sam, the normal space dynamic will actually introduce this like implicit Hessian gradient alignment such that you are near the manifold, you can actually prove that the gradient will always converge to the highest eigenvector such that it will be oscillating on this like two mode. So like it will always be either x plus v1 or x minus v1, where x is where x is the projection on the manifold. Such that so in this case, you can actually prove that like these two coincidence, more or less of coincidence, make sure that Sam is actually fallback Sam is actually doing what it wants to do, and that's because like this implicit bias such that the Sam will actually introduce this Hessian gradient alignment, which is like kind of non-trivial and at least not apparent from on the first sight. And this ends our conclusion of full batch stem. And the reason of the Hessian gradient alignment is too technical. And if you are interested, you can look at our paper. This involves a calculation on a convex function. So it's actually and it actually involves the calculation on a quadratic function nearby the minimizer. And there's also like some technical stuff that you need to do to actually control the error because the loss is not exactly a quadratic term. Uh, Meanwhile, we can also show that in our work, we also show another surprising result, which is that the first batch, the batch size one version of SAM is actually minimizing a completely different term, which is the average direction loss. In order to see that, let's consider a general regression problem where we first model our data by like there are just m data, and then each one of them need to minimize regression loss. And the loss is parameterized in the following way. There will be an input x, and there will also be there will be an x which is actually the weight here instead of the input data, and then there and the information about the data is contained in this function called fk. And then you can just imagine this means that inputting the case data point into your network. And then there will also be a label called yk, and the goal is to minimize a regression loss, and we will need to make some regularity assumption about L. So essentially, there are two assumptions. The first one is that the original regression loss must be the only minimizer of the regression loss will be the point where where the prediction matches the original label. And the second requirement is that at this minimizer the Hessian does not vanish. And this is satisfied by most of the common regression loss, for example, MSE or cross entropy. And finally, we need to assume the state of global minimizer of L with full rank Jacobian is actually not non-empty. This is more or less technical. And then we can now formally define the one SAM that I've been talking about. So essentially, your population loss is actually your training loss is actually just the combination of this K loss. And for the one SAM update, you will sample one loss at each step, where the K here is actually like a random variable that you sample at every step, and you will run the SAM update on this LK instead of the population instead of the global loss L. And again, we can see this nice two-phase dynamic. On the first phase, with small enough eta and rho, you can still prove that you will be approximately minimizing the original loss L. And on the second phase, you will be you can show a similar Riemannian gradient flow, but instead of minimizing the worst direction loss, you are actually now minimizing the average direction loss, which is the trace of the Hessian, instead of the maximum eigenvalue of the Hessian. And the first phase is roughly the same as before, where the second phase can be viewed in the following way, that one SEM can actually be viewed as an average of like m independent full batch SEM. And then like we already know that for full batch SEM, we can prove that like the direction the direction will be roughly corresponding to the gradient of the highest eigenvalue. So you only need to average over all the highest eigenvalue in order to get to the direction of the one SEM, and this will actually be corresponding to the trace of the Hessian because all of this like Hessian term of one data point is actually of rank one with on the manifold. So like the for this LK the trace and the highest eigenvalue is actually interchangeable. So this explains this equation. And we actually do some synthetic experiment in order to show our finding. And in fact, on this two-dimensional example, you can already see that one SEM and full batch SEM, and also a very particular example of like doing the SEM in the proper way, that you take the gradient of the gradient will converge into like very different minimizer. In particular, the one SEM will converge to a point where it's actually more balanced. And for full batch SEM, it will try to minimize the worst case, such that all the worst direction will be the flattest. And for the ascent direction, instead it will go to a point where like one direction is very sharp, but the other direction is extremely flat. Because this is what the minimizer will behave like. And finally, this concludes my discussion about SEM. And then eventually there's another work that I want to briefly touch here, that is about my work on rethinking sharpness. As mentioned before, we already showed that sharpness-aware minimization can essentially can be minimizing either the highest eigenvalue or the trace of Hessian in these two cases with different batch size. And then many algorithms actually will minimize one of them as well. For example, SGD with large learning rate will be minimizing the second term. And it also has been shown empirically that on some data set that the trace of Hessian has very strong correlation with the generalization, although the correlation may disappear or reverse in some other settings, for example, training vision transformer. Oh, actually, sorry. In some other setting, for example, training diffusion transformer. And there's perhaps one explanation to this, which has been shown in prior work, that there actually exists also sharp models with high sharpness, but with good generalization. But this hurt correlation. However, perhaps the real interesting question we care about is whether there is actually a causal relationship between the flatness. If you know that a minimizer is flat, can you prove that it will lead to better generalization? So this is a different question than asking the correlation. And you may imagine that the SEM, as SEM actually have good generalization property, you may imagine that SEM actually is an answer to this, as in the sense that like SEM will probably find the flat minimizer, as we show, but and it also leads to better generalization. However, in the second word that I'm going to talk about, we will actually show that this is not the case in general, that the flattest neural network can generalize better. While there have been positive results shown on simple examples, more or less linear network, we will show that if you only consider a very simple, a very simple architecture that contains a ReLU network with bias, and also a very standard data distribution, which is the 2-bit parity problem, where you have a d-dimension input, but the label is purely determined by the product of the first two terms. And under this setup, you can actually show that there exists a flattest minimizer that can predict zero on every input data point outside of your training set. Therefore, it completely it does not generalize at all. And also, if you run some experiment on this setup, you can also show that in this case, the SEM, which is on the right hand side, will actually find the point with very low sharpness, much lower than what gradient descent plus VDK will find, but also with a very low validation accuracy. So this means that SEM in this case actually cannot find a good generalizing solution, although it does in fact minimize the sharpness. And the reason behind this is that a two-layer ReLU network can be like purely memorizing your data. And here by memorizing, we mean that it first need to interpolate the entire training set, such that it's like 100% correct on the training set. And also, every data point need to activate only a disjoint neuron on the hidden layer. So for each data point, it will identify one neuron, and output of that one ReLU neuron will be like the label. After timing the second layer weight will be the label of this data point. And in this case, under the setup one, we can prove that there's a memorizing solution that is flattest. And also, like this memorizing solution have the property that once I input any other data point outside my training set, like all of this ReLU neuron will be like deactivated, and then therefore it will predict zero outside the training set. And this result can actually be extended to any depth D and input data set that are vertices of like complex polygons. And uh, and in this case, so in this case, uh, we actually show that the trace of the Hessian at least is not very well correlated with with the generalization. However, this is actually kind of subtle with respect to architecture. For example, if you just remove the bias and then consider the exactly the same data distribution, in this case, it actually becomes provable that like your like flattest minimizer has good generalization property, and then actually this only require a linear sample complexity in order for your flattest minimizer to generalize. And this result has been shown in like concurrent work as well, which prove that for a bias-free architecture, you can get generalization once you know that the minimizer is flat enough. And you can also show via experiment that once you remove the bias, the SAM will now find a point of very low sharpness and also very good validation accuracy. And finally, it like because we already showed that sharpness-aware minimization will be minimizing sharpness. It also has been shown empirically that they have good generalization. There's a question about whether their effect is purely based on sharpness, and the result is actually, in general speaking, no. As that we will actually show you an example where it actually finds the flattest minimizer that can generalize, while there exists like non-generalizing flattest minimizer. And this architecture is again very simple, that you actually just consider a two-layer ReLU network, but now instead you actually add an RMS norm between the two layers, and again the data distribution is the same two-bit parity. And in this case, you can predict similarly to the first setup that there exists a flattest minimizer that will predict zero on every input data point outside the training set. However, the SAM will actually find a point where the sharpness is very low, but it's actually still generalized. So it actually kind of managed to escape the non-generalizing flattest solution and instead find the generalizing flattest solution. This means that SAM, while we already try to prove that while we prove that it will minimize sharpness, and it also empirically does so, its benefit is not completely explained by sharpness alone. And in fact, there are some hidden mechanism that is like not understood yet about why SAM can generalize. And this concludes my talk. Thank you so much for listening. I'm happy to take any question.